So now let's say we're interested in subgraphs that are built by filtering on the subset of edges and vertices. So for example, the following one only contains people who are friends and who are more than 30 years old, right? So we just simply create a new vertex set, V2, by just taking only the older people, and then we are also filtering the edges by this, and then we simply create a subgraph, a new graph ring, G2. And we can just look at the vertices of G2. Of course, they're all more than 30, and these are the edges. And once again, we can just visualize this. There you go. So complex triplet filters. There's another example. So let's say we are interested in the particular pattern. So we have A going to B, and we call that edge E. And then we want to find subgraphs based on the edge E of type follow that is pointing from a younger user A to an older user B. Right? So what do? We just say my filter, I want the edge E relationship to be follow, and then I want to further filter by the age of A being less than the age of B. So these A's and B's are just coming from this find pattern. Okay, so now these are specific paths I'm interested in, and then I can use the paths that I've just found, and I can select e.source, e.dst, and e.relationship to create my new set of edges, right, that satisfy these conditions. And then simply use call my G2 to be a graph frame with vertices and these specific edges. So that gives me a different thing. So of course, you can do all kinds of things. You can now imagine you're consulting for LinkedIn and or whatever, or something like LinkedIn, and you can start quickly playing things, right? You can say, imagine throwing NLP on top of this. So you can say, whatever status update that someone did it contain say some post? Did the posts contain certain things like Apache Spark or Scala or whatever? Then you can essentially start creating subgraphs of people that have interest in some particular field that you're trying to, maybe headhunt them to hire them, right? So this is a standard LinkedIn problem. So all of these will fall in this class of finding subgraphs with patterns and filters. Okay, so, and those are my edges. Okay, so how's everyone doing? Now we're going to just shift gears into graph algorithms. I'm going to just hopefully crash course through. This is the full programming guide, so if you guys can do this, then it's good. You can have all the basic boxes ticked. So we'll get into breadth first search, figuring out connected components of a graph, strongly connected components. And we'll look at this class of algorithms that are called label propagation algorithms, typically used for community detection in a large graph. We'll do Pagerank using this vertex programming, which is nothing but the stationary distribution of that random surfer model I was talking about earlier. And then some shortest paths and other things like triangle counts. So these are all built-in methods, so nothing you need to implement yourself. Okay, so I strongly recommend, I can't embed these in place. I think GitHub.io rejects, like, I don't know, automated frame embeds, but So this is basically taking me to this breadth first search example. This is exactly where I'm pulling the code from. So what is a breadth first search? Oops. Okay, so generally we'll have a graph. This could be a tree. It could be some arbitrary graph with nodes and edges. I would start, so in my breadth first search, I'm interested in starting from somewhere and spreading out from that node to reach some other nodes of interest. So usually I'll have some source nodes and some destination nodes. And what I'll be doing is starting from the source node by going out, expanding out on the nearest neighbors, and then seeing if any of them are the destination nodes you're after, right? Because you're interested in finding the shortest path. And then you would simply go and keep expanding out and revisit. And you know, there's many variants of the algorithm, but basically it's some outward expanding bookkeeping. Okay. I think there's some animation here. So you start from A, move out, you reach B. You know the shortest path from A to B. Well, it's not even shortest, but yeah, you're just expanding out. Okay. So let's just look at a concrete example here. So the BFS is the method on the graph, the graph frame G. So now I have these two things called from expression and to expression. These are just SQL expressions, right? So the breadth first search finds the shortest paths from one vertex or set of vertices to another vertex or set of vertices. And the beginning vertex set and the end vertex set are specified by data frame expressions directly. So that's exactly all this is. So I'm saying I want my from expression to be name, that is Esther. So I want to start from a node whose name is Esther. And the to expression is I'm interested in going to all the nodes, vertices, whose age is less than 32. Okay, so then I do the run, and I can get my from and to, and this is the edge. Okay, so it's the shortest. And then here I have, I just added or name equals Bob. Okay, so it's just a different from expression. So now I have two source nodes I'm starting from. So breadth first expansions are very, very powerful projections of a very large network, because often you may be only interested in specific source nodes and specific destination nodes, and you're interested in finding paths in this graph that lead from source to destination, right? And this is a fully scalable algorithm. So of course we can start mixing in and do filters on top of this. So I'm only interested in edges that are where the relationship is not a friend. Okay. So then I'm also saying I'm only interested in paths in this breadth first search from Esther to others whose age is less than 32, but only these path lengths, shortest path lengths, are less than 3 or less. Okay, so then that's a good restriction, because it'll, first of all, not really, look for very, very long paths, because maybe you're not interested in them. And it'll also speed up things. Okay, that's a standard first kind of thing you would do on a graph. So the other main thing you want to understand about a graph, this is just a very basic geometric topological property of the graph, is how many connected components are there, right? Maybe the graph, so connected component is just it's defined in the case of an undirected graph. It's nothing but a subgraph where you can go from any vertex to any other vertex. Okay, So it means any pair of vertices are connected to each other by a path. This is an undirected graph. So this guy is one connected component, this guy is another connected component, and this one is another connected component. So you'd say this whole graph has three connected components. Okay, so this is very important. So often in Twitter, you will have communities that are completely disconnected. Okay, say in terms of retweets, or so if you take a retweet, which is A retweets B, turn that into an undirected relationship for a minute, and then look at the connected components of the retweet network of the whole planet and do it. It's okay. I'm pretty sure they'll be disconnected, right? People speak different languages and so on, right? Yeah. Here is yeah. So you this is something about checkpointing. So with graph frames 0.3 and later, the default connected components algorithm requires setting a Spark checkpoint directory, right? So checkpointing is something you want to do as a process. It allows you to truncate the RDD lineage graphs that are really under the hood when these algorithms are being implemented. So these RDD lineage graphs, remember the recipe that ensures fault tolerance, can completely grow out of control. And so you want to, you want to essentially use checkpointing to periodically, keep it in check. So for this, all we have to do from just an implementational point of view is you have to just provide a checkpoint directory. So set checkpoint dir to the Spark context, and then you can run this. So I'm just simply asking for all the connected components of G. Right. So although this is a tiny graph, there's a lot of setup. So it should run faster on a large graph as well. Okay. So this will return the connected components. Now, strongly connected components is the extension of the notion of connected components for a directed graph. Okay, so let's check this out, right? Because in a directed graph, ordered pairs of nodes matter. Ordered pairs matter. So so we say a graph is said to be strongly connected if every vertex is reachable from every other vertex, right? So reachable in the sense of directed path existing. The strongly connected components or disconnected components of an arbitrary directed graph form a partition into subgraphs that are themselves strongly connected. This is a consequence of the definition. So this is a graph with strongly connected components marked. So you can go from F to G and G back to F. And here you can get from any pair. So you can go from E to B, A to E, and so on. But you can't go from B. You can go from B to F, but you can't come back, right? So this is essentially strongly connected components. So there's three of them for this directed graph. Okay, so this ran. It took 44 seconds for a tiny graph. There's a lot of setup costs, so it should take roughly the same for a much larger graph. Okay, so what we have done here, we have put this new column called component. And the component just gets a long integer as its ID. Okay, so here I've gotten, so if you see the same number, it's all the same number. So all these guys are in one component. And Gabby is by herself. Okay, so that's for G. Okay, so now yeah, I have to specify, say, the number of iterations I want to run this, and I can get my strongly connected components enumerated as well with the component ID. Okay. So now there's several strongly connected components, right? This one, these three guys are together. Esther, David, Alice, and Bob and Charlie are together. So those are kind of maybe the first sorts of things you may want to do on a graph, if you can, usually. Okay, so label propagation. So what is this? So we have, it's a community detection algorithm. It's very quick, but but it's heuristic, just like k-means, right? So this particular algorithm basically has so it basically has this standard pattern like this. So every node will usually get its own ID, integer ID, unique ID in the beginning, and then in each step of the algorithm, the nodes will pass their IDs to their neighbors. Okay, in the vanilla version of the algorithm, everyone will receive the ID of their neighbors, and then they will simply take the median of the received IDs and use that as to update their own ID in the next step. Okay, so you basically do this sort of median updating. So now, initially everyone's unique, and you can imagine the median of the IDs of things that are connected together will start dominating, right? Now a lot of IDs will be dropped because only the medians are kept, and then you iterate this again. My previous median of my neighbors becomes my new ID, and then in the next step, I will be sending my ID to everyone, and others will be sending their IDs to me, and I do the median of my neighbors again. And that's basically propagating labels, right? So it has all the primitives of this Pregel model, right? You pass message, you receive message, you update your state. And then there should be a termination condition. Termination condition, simplest one is I stop if my IDs don't change. I've reached a state where all I get from my neighbors is the medians, and it's the same thing. And so if no one's ID changes, I stop. So that's kind of the basic idea. Okay, that's all heuristic. So here is running the label propagation with maximum of 5 iterations, and now I have some kind of a community ID label thrown on all these people. So let's look at it. So Fanny, David, Bob have the same ID, and Charlie, Esther, and Alice have the same ID, and Gabby is by herself. Gabby was a separate component, right? She was not even connected to anyone, right? Remember, she was one of the 2 connected components in one of the earlier things. That makes sense. Okay, so now we're moving into slightly more. So community detection is an example of this label propagation, but another really nice example of label propagation is Pagerank, okay, or this kind of Pregel bulk synchronous message passing thing, Pagerank. So I told you already, Pagerank can be seen as a Markov chain where you have this random surfer that with some probability 0.15 chooses any one of the existing web pages at random and jumps there, and the remaining probability 0.85. She only chooses the immediate out neighborhood of wherever she is and chooses one of those links at random and moves there. And then she kind of keeps jumping around like this And let's say every time she goes to a website, there is a counter, and she just hits the counter. So there's a counter keeping track of the number of visits of this random surfer. And then if you let her do this forever, let's say several billion times, then all these counters will increment slowly, right, in each of their nodes. Then you just divide that by the total number of hops she's been doing. That gives you what's called the empirical measure, the fraction of time she visited each node. And that essentially will converge to the stationary distribution of this Markov chain. Remember those eigenvalue things I showed you, the 2x2 case where you have this matrix, you square, and so yeah, this will be the largest eigenvalue corresponding to this eigenvector, and so the state vector here will be a bunch of numbers that sum to 1, and these numbers are sort of laid on all the nodes of your World Wide Web. So the more popular nodes will have a higher number or page rank. So that's the idea. So to do page rank, again, you're doing something very similar to this median process, but so it's slightly more involved. You basically keep updating your ranks, and then you stop either by setting some tolerance. So when the change in your rank is less than some tolerance, then you stop. And this is the reset probability, like what is the fraction with which you jump around like completely at random. So let's kind of do this. I'm going to probably break this, but what will happen now? Yeah, so you see now the page rank is all ones, right? Because what am I doing now? I'm just flipping a coin that's like, well, let's make this, maybe this will break. So this is a coin that always turns up. Okay, this is a coin that'll almost always turn up heads. And so when this happens, I jump at ooh, I broke it, as I said. Okay, it worked before, right? 0.99 thing. So what I was showing earlier was that when I have this to be a fairly large number that's close to 1, what I'm hoping, what I should get is that the page rank is a uniform, almost all ones, right? So all of them are equally likely have the same rank. Why? Because in my random surfer, the random surfer is just randomly surfing like crazy. It just jumps everywhere, right? So if I jump like crazy to every single node I have, right, I will visit every node with the same probability, right? That's why the ranks are the same. So, and remember I told you this is kind of one of these nice ideas these guys had, the Google founders, to put this 0.15 or some positive number, because that made the algorithm irreducible. That means you can actually talk about stationary distribution now, because there is a small chance, you'll never get trapped. You'll always be moving around, right? So anyway, this is your standard page rank reset probability and some tolerance, and I now know, who's the most popular, David or Fanny. They're both about the same. Oh, no. Alice, sorry. Alice is the more popular, right? Oh, no, sorry, Bob. Oops. 2.
Charlie.
Oh, Charlie. Damn, really? Oh, yes, good. Good. Yeah, so that's, yeah. I wonder what, so I increase the tolerance. This may take a long time. I don't know. Yeah. No, it's not too bad. So still Charlie is on the top. No, yes. Okay, so PageRank algorithm again is very, very powerful. It just tells you a lot about the flow of traffic on the network. Okay, so you can find the the results node has weights. So this one is the other way, which you may want to do for very, very large things. You cannot set this tolerance to be very small for a very large graph because it will consume all your resources. So you can set the maximum number of iterations you want to do. So the number of times each vertex will pass its current rank to its neighbors and start this iteration to reach the page rank. So you can stop this. So let's see, Charlie now is only 1.87, right? You see? So if I increase this to, say, 20, let's see, so Charlie hopefully will get to a bigger number, yeah? You see? Because I'm sort of freezing it in the middle of action, right? I'm just saying how many times they have to do bulk synchronous communication about their ranks too. Okay, so here is my result 3, which is now what I can do is I can personalize this PageRank algorithm for a vertex of interest to me. So I still have my reset probability, but I'm sort of now looking at the flow starting from node A, right? So this is from the perspective of A, so it's sort of personalizing it. Yeah, so now Bob has a higher rank. Let me just try to make this. Yeah. So if I have my initial condition from A, this is essentially how what will happen after 20 iterations of this. This is very useful because you may want to have a personalized view on how how information is flowing on your network. It's random surfing way. Okay, so shortest paths is the other main thing. So we want to compute the shortest paths to the given set of landmark vertices. And so landmark just means we are interested in some special vertices. We call them as our landmarks. And what we're interested in is the shortest path from every vertex to the landmark vertex. Okay? And in fact, this is exactly what I'm doing to define the ideological tree from Twitter using retweets. Exactly the same algorithm with some changes, some hand-built changes, but almost the same. Because, for example, I can ask, say, in the British election, we were monitoring it, and we took Theresa May as one of our main person we were tracking, and also Jeremy Corbyn and a whole bunch of political bloggers and newspapers and things like this. So we just sort of watched it for 4 weeks around the British election, and the computation actually that was running yesterday, it was doing exactly this. So what we did is we built a retweet network. So every user and every other user. So if A retweets B, say 12 times in this 9-week, 4-week period, then we put some weight on it, right? Some integer weight on it. And that gives me my weighted network of who retweets who. Then I can take that weight, and then instead of having a big number, I can just do some transformation like 1 over 1 plus the weight. So now a big number becomes a small number. Okay, there is a probability model behind it, so I'm not just pulling magic, but let's ignore that for a sec. So now I can actually talk about the most retweeted path along this network from, say, some guy, some A, to some landmark. Say Jeremy Corbyn is my landmark, and Theresa May is my other landmark. I'm interested in all these people that were in this network, several million. What is their shortest path? So now my most retweeted path becomes my shortest path because of this 1 over 1 plus number of retweet transformation, right? So I immediately can use these shortest path, and even with just 2 landmarks, because they represent the 2 ends of the British party system, right? I can kind of start classifying people, right? Just saying what is the shortest distance to Theresa May or Jeremy Corbyn for every person in the population. That gives me some kind of feature, right? The minimal number of retweets I need to do to get to these people in the most retweeted path. So that kind of profile immediately gives me some way to talk about distances between people, right? So then I can just use pairwise distances, just like you do in phylogenetics or population genetics. So I can take the L1 distance between these path links to various landmarks, and then I can use these pairwise L1 distances, which is the absolute difference between the links, right, to the landmarks. And I can just use that in the neighbor joining classical algorithm. So I can construct a tree for the whole population based on their the length of the most retweeted paths, just the sort of shortest paths to each of the landmarks. So that means, in general, given a bunch of landmarks in any weighted graph and some notion of shortest path, I can actually define a tree that classifies the population. Okay, so here's the shortest path. It's very useful. So let's just quickly do it. So here I'm defining my landmarks to be a sequence of vertices. Okay, so I just say I'm interested in A and D. My vertex IDs A and D as my landmark. So I'm interested in the distance from every vertex to A and D. So here, in this case, Esther, the shortest path to D is 1. The shortest path from A is 2. Okay, and in these cases, it's empty because the path doesn't exist. Okay, so this is. And triangle counts, again, is another implementation. So these are the default ones. So in fact, when we did this thing, we had a slight modification of the existing shortest path algorithm, and it's not that much. Because the reason is we're not just interested in the sum of all the paths along the shortest path. We actually wanted to keep the full path, right? We wanted to keep all the details in the path itself. For other reasons, for mathematical reasons. And it's a slight modification of exactly the same Pregel API. So we're not changing the Pregel model of bulk synchronous communication. We just decide a slightly different message is passed, a slightly different state is updated, and then you can do quite a lot in this framework. Okay, so triangle count is another one. So we can just count the number of triangles. Okay, so this just tells me the number of triangles passing through each vertex. So let's see. Esther has 3 triangles passing through her. Oh, sorry, 1 triangle. Okay, so I think kind of given you I basically reparsed the user guide. Okay, there's a lot more here, but I think you have some ideas of what's possible now. So what I wanted to do next is show you guys. This is actually an assigned homework assignment. It's kind of a fun assignment. So it involves some watching the video. Okay. What I would like, I mean, Tilo and I will talk about how to turn this into an assignment, but all the answers are here. We may add some extra questions, but what I would like you to do is watch this. I'm not going to check whether you watched it or whatever. I mean, so you have to sign up for Bright Talk. It's free. It's actually from Joseph Bradley. So I won't play the whole thing, but he's going through everything much more slowly, and I really recommend that you go through that. When you go through that, I think that's all done in Python, I believe, and so this is redone in Scala. pure Scala. It has a little bit extra stuff, putting some more D3 magic on it, but generally it's the Scala version of that talk, I think. And it's a this is why our archive is huge now. This file alone is 1.2 MB. So it has quite a lot of data on flights and delays and things like this. So it's a very good. So syntax-wise, you're covered. Concept-wise, you're covered. You kind of know enough to dig into this yourself. And I checked that everything works today. So yeah, so play with this and try to understand it. So watch the video first. And I think, yeah, I'm not sure if they did this or we did this. I don't really remember now. They do use those views. So in the end, we use, yeah, it's just going through the same algorithms, but in a more interesting setting. Yeah, here you have to, you know, don't forget this. This is a big thing here. I just fixed it this morning. So you should be able to now mix the, you know, the analysis. So this is some graph frame processing, filtering, finding patterns, and then you're now displaying in this sort of interactive D3 type thing. Right? So you have to read this, at least spend like 2 hours. Watch the video, you'll understand it. And this kind of thing is what you would like to do in the end when you communicate your ideas to some, you know, your boss or your potential client or whatever, right? You need to make it also very simple. Right? You don't need to have Wikipedia embeds and stuff like that. So this is, you know, sort of, it's important to have visually appealing presentations of complex ideas. Okay, so that's, yeah, so this, for example, so you can say, well, I'm easily able to visualize delayed trips that are departing from the west coast of the US, okay? So you can just say, oh yeah, so these are my delayed trips from various airports on the west coast, right? So this is nice. And you will see how everything comes together. So now let's look at, so I'll say this is basically homework. So my plans for, so we have 2 more weeks left or 1 more week left? 2, okay. So my plans are maybe next week I'll do structured streaming because that's the other main, the 4th component of Apache Spark, right? So we did SQL. Machine learning library is huge. I cannot do the full programming guide. We'll be sitting here for a whole semester, like 17 weeks, just going through every. So we've touched on main top aspects of machine learning library, and graph frames pretty much exhaustively we did today. You need to get your hands dirty with that example. The next main one is structured streaming. So once we have that under our belt next week, then the following week I could go into more text analytics. We'll see how it goes, right? Because we've been heavy on regressions recently. Yeah, or we could do something else so that you guys are better prepared for your projects. I don't know. Should we dig into bioinformatics or you could dig it in and do like what Yevgen did, right? Can you?
I was thinking about doing this.
That'll be good.
I haven't got time yet, but we'll try to do it maybe for next week.
Yeah, I think that'll be
they
good.
They have this nice tutorial on 1,000 genomes.
Okay.
I went through it, but I haven't.
There you go. Yeah, that would be good. In fact, then. Yeah. So I won't read it at all. So I haven't really read it. Then you can show me, and I will try to learn from you. Right? That's. Okay. No, I mean I think that's kind of the point here. So we should quickly reach a stage where you know you will know more than me, and that's important, right? Then we can. Oh, in terms of projects, like in the last minute, if you're interested in projects but you don't quite know what to do, I have a few projects that I can show you or talk to you about. but I strongly encourage you to, do your own thing as well. So it looks like we won't change the timing. That's probably, Is anyone else here burning to go to reinforcement learning? No. Okay, good. So then let's just forget about it.